Morning, everyone. Thanks for the introduction and thanks for the invitation to the workshop. Yes. Trying to get this. Okay. All right. So what I would like to do today is not so much give you answers or results, but rather ask questions. And my hope is that through asking those questions, we may hope to at least start towards understanding better what deep learning is. But really, I think the key point here is, and the key message that I want to pass today is, we face this puzzle, right? Historically, people have observed that there are certain surprising facts with deep learning when you train deep networks, and the immediate reaction was, well, that's really new and different, and we don't understand anything. We need a new theory or a new approach. I guess my point today will be to try and show you that some of the ingredients that we see in deep learning now are actually not so new and actually reminiscent of things that we have observed in older algorithms before. And so by looking at those older algorithms and what does it mean to understand those older algorithms, we may better understand what are the right questions to ask for deep learning and what does it mean to understand deep learning. So I will start by listing some of these surprising observations and then compare to these older algorithms and then give a list of theoretical questions and with partial answers when available. So let's start with basic definitions. So deep learning, at a very high level, you can think of it as a very powerful tool to learn functions from high-dimensional space to potentially high-dimensional space as well, from samples. And the good thing is that it's very expressive. You can have very large networks that can represent very complex functions. You can also embed a lot of prior knowledge in some sense in the structure of the network. It's parametric by essence because you have a finite number of parameters. And you can run it at large scale. We have powerful and efficient algorithms. In this talk, I will focus on classification, which is kind of the most puzzling, or the simplest case, but also the most puzzling one. And I assume, as usual, that a deep network is basically a succession of layers where you have linear map followed by a nonlinearity. And the training is performed by doing gradient descent over all these parameters, by minimizing something like the loss. Okay, so this is just basic standard stuff. Now, first observation. This is actually maybe let me move the mouse away. This is by now a classical paper, and the first observation is that, well, if you train a neural network, it's possible to reach very low training error, like zero training error, let's say. and that's what the curve here shows. As you train, the training error can go to zero, even if you shuffle the labels. You take a data set, and you instead of taking the original labels that are in your data set, you shuffle those labels. That means you completely destroy the relationship between the input and the output, yet you still can fit that data set, even though it's a very complex function, essentially, that you're fitting. So you can train to zero training error. And what happens is, when you look at the test error, well, the test error, this is as a function of the noise that you introduce in the label corruption. Of course, if you corrupt completely the labels, then you can't predict anything. The test error will be as bad as can be, right? Like this is a data set with 10 classes, so the test error is 90% here. Whereas if you don't corrupt the labels, you get good generalization, basically. So that's the message. So essentially the conclusion is, well, you can fit arbitrarily complex functions. And so that means your network has a very high capacity. And yet you can generalize. So you can have training error 0, which means the test error is equal to the generalization gap between the difference between the training and the test error. And as we've seen, if the target function is reasonable, like you have a normal image classification problem, you have a low generalization gap. If the target function is messy, you have a high generalization gap, even though you still have the same capacity in both cases. So that's considered puzzling. And even further, if you look more into the details, you have two kind of losses, right? Like you have the loss that you minimize with your algorithm, what is called the surrogate loss or the proxy loss. And then what you actually measure usually is the misclassification error. And what happens is that you can overfit the surrogate loss. Like you can see the test surrogate loss go up if you keep iterating. And while the test misclassification error will not go up. So that's another kind of puzzle. And the last observation is that there are many factors that influence this behavior and the quality of your solution, the test error. One is the initialization. There is some sort of optimal scale. If you start with too large weights, it won't work. If it's too small, it won't work either. The learning rate plays a big role also. You have to, choose it right, or maybe decrease it in a certain way over time. The size of the mini batch also plays a role. If you have a very large mini batch, you get worse solutions than if you have a small mini batch size. And the last thing is that if you have overparameterization meaning like large layers, like large number of parameters in your network, and possibly even much larger than the number of samples, actually it doesn't go wrong, right? Like things still work, and actually they work even better. If you overparameterize, optimization becomes easier in some sense, without leading to overfitting. So these are the observations. Now, let me summarize. Essentially, like, of course, I'm simplifying just to keep the ideas highlighted here. Essentially, we can get zero training error, but we overfit only when there is no structure in the data, right? That's observation number one. We can overfit on the surrogate loss, but not necessarily on the misclassification error. And, well, because the algorithm is iterative, right? We don't have an explicit criterion that we are minimizing. Although, I mean, we know we're trying to minimize the loss, but we don't know whether we reach the global minimum of that function. So there is some mystery around what exactly is the algorithm doing, and in particular, does it regularize, and what does it regularize? Yes?
So on this rethinking generalization paper,
yes,
was the number of training example smaller than the number of members roughly? So, and the question is, let's say you would train on a billion of examples with random labels, could you really get to zero training error?
Well, if you have too many examples, then yes, you will reach the limit of the capacity of your network. So you need a large enough network so that you can get to zero training error. So yeah, I would say by definition, if you can fit arbitrarily labeled data, that means you're over-parameterized in a way, because you can fit anything from the point of view of this limited data set. Right? So now the question that I want to ask is that new? And the point is, we actually heard some of that before, at least if you're old enough to have been in this field for more than 5 to 10 years. And so let's look at all the algorithms that actually have the same properties. Let's start with the simplest one, k-nearest neighbors. So k-nearest neighbor essentially stores all the training data, right? So that means you can get zero training error by definition. I mean, okay, depends how you want to define the prediction on the training data, but you can say, well, on the training data will just predict what I have stored. So that means I have zero training error, right? So this we have seen. And the point is, same thing, like if you run on the same data, you would have the same behavior. That's like if you have no structure, like if you randomly shuffle the labels, yes, you will overfit. I mean, or in the sense that the test error will be very bad when the training error is 0. And if you have some structure, you might recover it, so you may generalize. So this is not really new in some sense. But okay, there are some differences still. One thing is that we know that there is some sort of regularization going on because we use k nearest neighbor, and like, you know, if you smooth over more neighbors, then you have like a smoother solution in some sense. The other thing is that it's non-parametric. We store all the data, so there is no definition of a class of function over which we try to minimize something in this case. And there is not even a training algorithm, right? Like we just store the data, so it's not really training. So it's still a bit different, but at least this aspect was seen in this case, right? Now let's look at another algorithm, SVM. So in this case, it's trained by gradient descent usually, not stochastic gradient descent, although there are some stochastic versions. And it also has a very large capacity, like the class of function that you use in SVM, especially if you use, say, the Gaussian kernel, has infinite VC dimensions, so you also can fit very complex functions. And, well, okay, I would say, although, you know, it's not as clear-cut as in the case of k-nearest neighbor, where you have training error 0. In the case of SVM, like on the complex data set, you may not get training error 0. But I would say that somehow the same behavior happens, that you can, it generalizes when it can, despite this large capacity. But in this case, of course, you can say, well, we understand really well why, because there is explicit regularization in the case of SVM. You minimize the norm of the waves. It's also non-parametric, and there is a convex objective. So it's kind of, yes?
So you say it's non-parametric, but isn't it the case that if you just take the eigenfunctions of the kernel, you effectively have all your finite parameters?
Yes, well, so non-parametric, okay, I'm using it in a somewhat loosely defined way here, is like whether you have a finite number of parameters independent of the size of the data set, or whether the number of effective parameters grows with the size of your data set. And in some sense, like with SVM, if you have a bigger data set, you have more, alpha values, right? Like more weights. So then you have more parameters that you have.
By definition, every linear algorithm is non-parametric.
No. So in the primal form, primal form is parametric. The dual form is non-parametric. That's what I mean here. And if you have a nonlinear kernel, you're in the dual. So then you are in this non-parametric. But I agree, it's not a very clear-cut separation.
And the primal is parametric in infinite dimensional space.
Yes. So yeah, it's also non-parametric in that way. Yes.
But I think for SVM, so the paper you mentioned also shows that you don't do explicit regularization for SVM, it still can generalize.
Yes.
Natural data. So it's sort of you could throw in the regularizer and sort of say this is why it generalizes, but if you remove it, it still generalizes. So it's also a little bit.
You mean if you don't penalize with the weight vector?
Yeah, Gaussian kernel without.
Right.
It still works.
It depends on the exposition.
Sorry?
It depends on the exposition of it.
So then it depends on the opposition.
Right. Yeah, and I'm just saying, like in the case where you have the normal SVM algorithm, you could say, well, we understand because we have the explicit regularization. If you are in the case where you don't have explicit regularization, but somehow the regularization is hidden in the algorithm, then you're back to more the deep learning style. Another one, boosting. And in boosting, this is also a relatively old paper. This is where the first time was observed this behavior that you have an iterative algorithm, and as you run it, here you have the training error, and here you have the test error. You get to training error 0 at some point, but you can keep running it, and as you keep running it, instead of overfitting, as you would expect, well, then the test error keeps going down. And this also has to do with, this is the misclassification error, not the surrogate error. So that's like this other behavior of surrogate versus misclassification error. So, just to summarize, so this is trained by an iterative algorithm, like in deep learning. It has large capacity because also like the class of convex combination of simple classifier is infinite VC dimension. It gets to 0 training error, and it also generalizes when it can, right? And it doesn't overfit on the misclassification error, even after reaching 0 training error. But you could say, well, it's also non-parametric because of the same reason. You can have infinitely many parameters in your convex combination. And it's not really using SGD, like stochastic gradient descent, it's doing coordinate descent more. So it's a bit different still. Okay, so, just to summarize, right, like there were these 3 observations, and my point is that we all have seen those observations in the past, in different flavors, in different forms or different combinations, but we have seen them. And we have explanations for them, like, okay, sometimes more theoretical, sometimes more end wavy, but we have explanations. And the point is, we feel we understand those algorithms. I mean, I don't think people would say, oh, boosting is so mysterious, what's going on? Or, I don't know, SVM, what's going on? No, people would say, well, no, there is a well-founded theory about all these algorithms. So why is that when we have an algorithm which presents the same properties, suddenly we say, oh, my God, what's going on? So let's look a bit more at the details. Okay, this is a bit of notation, but it's basically a standard thing. The setup in which you study this algorithm is usually that you assume that you have IID pairs sampled from some unknown distribution. In this case, we have like classification, so I'm assuming the y, the label is -1, 1. Eta denotes the so-called regression function, which is the probability of being 1 at a given x. And then you have a classifier which I take as a real valued function. That's often the case that, like, even though you're doing classification, you still assume your function is real valued, and then you consider that this function makes an error when the prediction has the wrong sign, right? Like it's not the same sign as y. And so that's how you define the misclassification error. And then you can define an optimal classifier, and the optimal classifier among all possible functions is the one that has the sign of eta -1/2, right? Like when the probability is over 1/2 of being 1, then you predict 1, otherwise -1. And so there are like typical questions you may ask for your algorithms are like the simplest one is the one of consistency, right? Like if you have enough data, will you eventually reach the optimal classifier? Right? That sounds natural, but often it's not even asked in the case of deep learning, which is interesting. And then, of course, you can go deeper and you can ask for convergence rates and generalization properties and so on and so forth. And now let's split the theory or the kind of analysis into 2 parts, the parametric and non-parametric. Again, apologies for the kind of loose definition of parametric versus non-parametric. Here, I mean, like if you have a fixed known class over which you're optimizing, or maybe like a sequence of nested classes, then like you typically ask those kind of questions. Like if you have a fixed class, usually you assume that for the purpose of the analysis, the algorithm may be doing something different, but for the purpose of the analysis, you're assuming that your algorithm picks the ERM, empirical risk minimizer, like the best empirical in the class. And you may ask questions about, say, learnability, meaning that is your algorithm, like the ERM, does it compete with the best in the class LH? And at what kind of convergence rate do you get? And then like the next question you ask typically is approximation versus estimation. If you have that class and you pick the best in that class, you can control what is called the estimation, right? That's this quantity here. But then there is the question of how good is the best in that class, and if you grow the class, then you will eventually contain the base classifier. So the class will be big enough to approximate the true function. In the non-parametric case, where you don't have a clear function class over which you're minimizing, then typically the thing is reversed. You start with the algorithm, right? Like you have the algorithm, you don't know what the class is doing, the class of function is, and you ask questions like consistency, right? Like if I run this algorithm enough, will I get to the base classifier? And now you can say, well, if you have a regularization parameter, like in K and N, if you have K as a parameter, you can say, well, if I fix K and I let N go to infinity, what happens, right? And then you can do also this game of approximation estimation, where you can see what happens when n goes to infinity for a fixed k, and then see what happens with k increasing, and like having the right trade-off will give you rate of convergence. But for this trade-off to make sense, you have to assume something of on your target distribution. Like if you make no assumptions, then the no free lunch kicks in, and basically you cannot have rates of convergence that are universal without any assumption on the distribution. Okay, so this is just broad overview. Now let's look at the kind of result that exists for this algorithm that I mentioned before. So k nearest neighbor. So we know what is the asymptotic error rate of a k nearest neighbor classifier. Like if you have infinitely many data for a fixed k, then you get like for the one nearest neighbor classifier, you know that it's worse than the Bayes classifier, but better than twice the Bayes error. So it's fairly close. And if you increase k, you get closer and closer to the Bayes classifier. So when k goes to infinity, the optimal or asymptotic error of the k nearest neighbor goes to the Bayes classifier, which is a good sign. And you can even quantify the difference between the asymptotic error of k and n versus the Bayes error, and it's of this form, like 1 over square root k. All right? Now, of course, this is asymptotic. So then, like, you want to know how this happens, and basically it's captured by this theorem here of consistency of a nearest neighbor. If k has to go to infinity to approximate the Bayes error, but not too fast, right? Like it should be such that k over n goes to 0. That like the neighborhood over which you average your labels has to shrink as you increase the size of your data set. And under those conditions, you can have consistency. And then there are results about, we understand fairly well the geometry of this algorithm, and in particular, like the rate of convergence of the KNN to the Bayes classifier is determined by this quantity that I did not completely spell out here, which is like the measure of the region around the decision boundary, the Bayes decision boundary, such that the Bayes decision function is close to being 1/2, right? Like if there is a big region around the Bayes decision boundary where the decision function stays, or the regression function, stays close to 1/2, then it's very hard to pinpoint exactly where the decision boundary is, so you go slower. But if it's very clear where it is, and you have no noise basically, then it's much easier, and then you can get faster rate of convergence. So let's say this is fairly well understood even at this level of detail. Now let's look at SVMs. So SVMs, okay, maybe at a high level I won't go into the details, but what we understand is that there is regularization. That regularization is what allows to control the capacity of the class of function over which we are minimizing, right? Like you can say, instead of minimizing the error plus the norm of some of your function, it's equivalent to minimizing the error within a ball and growing that ball, right? And minimizing the error within the ball, we know roughly how the capacity of the class determined by the ball in the RKHS behaves. And so you can play also this game of estimation approximation. You can see, like, as you grow the ball, you approximate better, but the estimation gets worse, and you can trade all those things. Okay. For boosting, it's kind of the same. Whereas there is some implicit regularization in this case. The regularization is more the L1 norm of the weight vector of which is the convex combination of simple classifier that you use. And like, unlike SVMs, the regularization is more implicit, but you can show that the way the iterative procedure is implemented, it will have a regularization effect, which means like restrict the L1 norm of your convex combination classifier or maximize the margin, kind of equivalent. And we understand also the capacity of this convex combination of classifiers based on the structure of the class of the base class of classifiers. So again, this is fairly well understood. So now, okay, going back to deep learning. Yes?
So linguistic, would you say we really by the margin is this graphic form put out at the beginning that although we are sometimes in totally overfit surrogate loss, the actual loss, the classification loss is going to zero. So you feel that you understand that?
Well, at least we have a good handle on it. Yeah, I would not claim that we completely understand what's going on in boosting, unlike maybe 10 years ago, where we have a very precise understanding. In the case of boosting, at least we have a good idea of what's going on. I agree that the proof that the iterative algorithm does, meaning is equivalent to regularization algorithm, is a bit end weighted, right? Like you can't really prove that it's strictly equivalent. As a result, indeed, the connection between the surrogate loss and the true loss in the case of AdaBoost, I mean, in the case of the regularization, we understand better, but in the case of AdaBoost, we may not understand as well. Yes, I mean, of course, I'm simplifying with this, but my point is that at least in the case of boosting, we have, like, at least I never heard someone say, well, boosting is so magical, we need a new theory, right?
I heard Bryman say that, because I wrote enough for that, but he wasn't satisfied with this margin surrogate loss thing. He said the theory is not satisfied.
Right. Yeah, I mean, of course, there are still more things to understand. All right, so let's go back to deep learning. So I guess maybe that's trivial to say that, but my point is that deep learning generalizes despite having a large capacity. So that means there is some implicit regularization. So the point is really how do we understand what this implicit regularization is, and like as a result, like what does this regularization imply? Like what kind of functions would we learn easily versus not? Meaning that what kind of functions does the algorithm prefer? Maybe I'll skip that. and so maybe I don't have much time left, so let me accelerate a bit. So let's look quickly at the optimization aspect, right? There is this question of what are we optimizing? Like, do we get the global minimum? Do we get the local minimum? What is the property of this local minimum, and so on? The point is that when you have overparameterization, when you have a very large network, it turns out that the optimization becomes easier, and like there are actually, well, there is a beginning of a theoretical understanding of this phenomenon in the sense that, at least for linear networks, for example, we know that if you have an overparameterized network, you have, and you take level sets, then you may have only one connected component. So that means you have only one basin of attraction in some sense. And you have no poor local minimum, and you can show that under certain conditions, all the local minima are global minima. But of course, yeah, maybe as you increase the size, the number of parameters, estimation becomes harder, but then we know that there is some implicit regularization that avoids that. So my point is that to a large extent you can say, if you're over-parameterized, then the optimization problem is kind of easy, so you don't have to worry. You can even assume that you get to the something like the global optimum. And so now the question is, where does the regularization come from? And these are 4 places where there is regularization, that there can be regularization going on. One is the initialization, how you choose the initial weights. Then one is the fact that you have, when you do gradient descent, you make discrete steps. So you may, so that means there is a certain way of following the gradient that may have effects on which place in the in the global minimum you reach. Actually, yeah, because I forgot to mention, but we always think of one global minimum, but there is no one global minimum, because if you are over-parameterized, all the minima are degenerate. So you have infinitely many, in the sense that you have a variety of minima that are all equivalent. I mean, maybe there is one single connected region which is the global minimum, but it's still not a single point. And where you end up in that region may depend on the dynamics of the gradient descent. And of course, the noise in the stochastic gradient descent may also determine or affect that convergence. And you may have other forms of noise. There is this story about flat minima, which tells you that, like if you play with these parameters, you can influence whether you get to a minimum that is surrounded by a very large region of equal value, or in the loss landscape, or whether it's a sharp minimum, which means that as you move away from your point, you get much higher values of the loss. And this is you can explain it partially with these things, right? Like if you have if you have a large basin and you initialize randomly, then you have a higher probability of starting in that large basin than if it's a small basin. So that's kind of natural. And there are other explanations of how these different things that I mentioned influence whether you reach a flat or a large minima. But the problem is that we don't really have a convincing theory about how the flatness of the minimum influences generalization, apart from hand wavy Bayesian style explanations. One thing that I want to mention, which is actually related to initialization. This is, yeah, that was recorded, yes. Sorry. Yeah, so, okay, this is a simple experiment which shows an interesting phenomenon. If you take a radio network with one hidden layer, and you initialize to, like in principle, and you try to fit, this is regression, not classification, but just for the purpose of illustration. If you try to fit those points, in principle, you could reach a solution that looks like this, because the radio network is just a piecewise linear function, and if you have large hidden layer, you can have a very complex function. This function has zero training error, so it's it's a fine function. Now, if you initialize with very small weight, then what you'll see is that you get to some very simple function like this. And actually, you can show that the dynamics of the stochastic gradient descent, or gradient descent actually, even not you don't even need the noise, will lead to such functions when you initialize small. So there is a quantization effect implicit in the behavior of those networks. But as I'm running out of time, maybe I'll switch to, I'll go directly to the conclusion, because I think the main point was really, there are these behaviors that we have observed before, so we should not consider that everything is new and different. We should dig into what we know about these older algorithms, even though we may not understand everything about them, but we do understand quite a bit. So that's something that we could import and use in the context of deep learning. But the other aspect is that we should see really, I think that's my other main point, we should see this algorithm as a non-parametric algorithm. I think that's a better way to see it, and forget the fact that you have a large number of parameters, just assume you have infinitely many, because you can make your hidden layers are as large as you want, and still things are manageable. So, and if it's a non-parametric regime, then that means we don't want to understand the capacity of the class of function. That's not in non-parametric cases, you don't even know what the class of function. So let's imagine that we are in this situation, and let's focus on what the algorithm is actually doing in terms of regularization. Let's try to understand the different aspects of that regularization, this example that I showed you. Why does it converge to such solutions and not such solutions? Right. And then that means the kind of analysis that you do in non-parametric setup is that you try to understand which are the classes for which your algorithm reaches a minimax rate of convergence. And that's what tells you about the properties of your algorithm. Because if you say, well, I know that when the class of function or the target function is so-and-so, it has such smoothness property, then my algorithm is minimax, that means your algorithm implements some sort of bias towards such functions. So that's what we should be trying to understand in my view. With that, thank you.